The purpose of the ramp lab was to determine a graphical and mathematical relationship between position and time. Now, the variables we were looking at the relationship between time, measured in seconds, and position measured in meters. Now, when we ended up graphing that relationship between position and time, we ended up with a relationship where position was proportional to the square of time. Now, if we were to look at Google Sheets, Excel, or like a regression from a graphing calculator, we would end up with some exponential relationship, which is not super easy for us to interpret and to generalize. So what the plan is for right now is we're going to look at a velocity versus time graph, and then try to use our understandings of velocity time graphs to produce a mathematical relationship between position and time that can be used for any object with uniform acceleration. So if we're going to be looking at a velocity versus time graph where we have a constant uniform acceleration, that means that on a VT graph, we would end up with a constant slope. Now, because we're trying to figure out a relationship between position and time from this graph, we need to be able to determine position from this. Now, what we do know is that displacement, which is a change in position, is the area between the curve and the time axis on a velocity versus time graph. Now, that was super easy for us to calculate when we had an acceleration of 0. So when the velocity was constant, we had that horizontal line. The area between the curve and the time axis was a rectangle. Super easy to calculate. However, this shape is not so easy. So the way that we're going to need to break this up is, well, we can do one of two ways. One way we could do it is just put this graph on an actual graph paper, and then try to figure out how many boxes there are under the curve in the area of interest. Now, for this case, I may have chosen a grid that was a bit too large, but if I were to shrink the size of each grid, well, it's a little bit easier for us to determine the number of boxes under the curve. And then if I were to make it increasingly smaller, well, eventually at a certain point, it would be small enough for us to just count up the number of boxes and then figure out the sum of all of those in the area of interest to figure out the area under the curve. Yeah, at this point, this might be sufficient to do that. But honestly, looking at that, there would be quite a large number of boxes to count up. And then, even then, it still would not be perfect. So I might need to approach this another way versus just counting up the number of boxes in the area under the curve. So the way that I can do that is by setting up some variables. Let's say I want to look at the change in position, that displacement from an initial time to a final time, ti to tf respectively. I have a function where we have some starting velocity. In this case, it is a starting velocity greater than 0 meters per second with a constant positive acceleration. Now, the way that I can do this is I can try to determine an equation to figure out the area of this shape. Now, I don't know the equation for this shape off the top of my head, but one thing I can do is to break it up into two shapes that I do know. I know how to calculate the area of a rectangle, that bottom shape, and I know how to calculate the area of a rectangle, that top shape. So that's exactly what I'm going to do. I'm going to figure out the area of the rectangle, which I'm going to denote as A, and then the area of the triangle, which I'm going to denote as area B. And then once I have those individual areas, I'll add them together to figure out the displacement within this time interval. So I'm going to be focusing on area A first, which is that rectangular region. So delta x, subscript A, that is the change in position of region A. Now, we can figure that out from the area under the curve on a velocity time graph. Now, because the shape is a rectangle, we can calculate that by taking the height times the width, which is the area of a rectangle. In this case, our height is just going to be the initial velocity, vi, in that region, minus the velocity at the time axis, which would be 0 meters per second, times the width, which would be my final time, tf, minus my initial time, ti. So this is where the height is from 0 meters per second to the velocity at the initial time, which is ti. I can simplify this down, so that way my displacement of region A is equal to my initial velocity times my change in time. Now, to calculate the area of region B, that triangular region, well, that's just going to be 1/2 height times width. That's the equation for the area of a triangle. In this case, though, my height is going to be calculated a little bit differently. The height here is final velocity, Vf, minus initial velocity, Vi. And I multiply that by that same width, which is my final time minus my initial time. Now, the reason why my height is different here is because I'm not measuring the height from the time axis, just from the region that has not already been determined for its area. Now, final anything minus initial anything would be change. That's why I have, from my calculation of displacement of region B, 1/2 times the change of velocity times the change in time. Now, one thing that I also know, though, is that our average acceleration can be calculated by taking our change in velocity over change in time. I'm going to rearrange that and then substitute it in for the change in velocity in this step. Now, I can rearrange that equation, which we get from the slope of a vt graph, by just multiplying both sides by delta t. So our velocity, or change in velocity rather, is equal to our acceleration times our change in time. So when I plug that in for my delta v term, right over here, I end up figuring out that the change in position of region B is going to be 1/2 times my average acceleration times my change in time times my change in time. I can simplify that down, so that way the displacement of region B is 1/2 a times delta t squared. At this point, I have two simple equations to explain how we can calculate the area under the curve within this time interval. Next step is just to add those two values together. So the total displacement is the displacement of region A plus the displacement of region B. The total displacement is the sum of all parts under the curve. So I substitute then those equations from up above. But because I'm trying to figure out a relationship between position and time rather than displacement and time, that's why I'm breaking up my delta x on the left side of the equal sign into final position minus initial position. Just so that way I can try to rearrange this to just get my final position as an isolated variable on the left side of our equal sign. To do that, I can add initial position to both sides. This right here is a great equation if we are starting off from any time and we're looking at our change in time, where we know the initial velocity of this time interval, the acceleration, and then once again, the change in time. However, quite often, we're going to be looking at, well, an initial time of 0. So if we were to account for that, ti would be equal to 0 seconds. This is where we end up plugging in, for the i's, 0. So instead of xi for the initial position, it would just be the position at 0 seconds. Instead of initial velocity vi, it's v naught, which is the velocity at 0 seconds. Instead of having a change in time, which would be final time minus initial, it would be your final time minus 0, which would just be whatever time we're calculating for. And then instead of, once again, the delta t squared, it's just going to be t squared. This would be an equation that you can use when we have a uniform acceleration, where we are starting off with an initial time of 0 seconds.